Ocean motion. And in this section, we're looking at 3 different ways that the ocean water moves: currents, waves, and tides. So we're going to start with currents. Ocean currents are movements of ocean water that follow a regular pattern. And a lot of people describe these as little rivers in the ocean. Now within currents, we actually have 3 different kinds of currents. The first one is called a surface current. Surface currents are a horizontal movement of ocean water caused by wind, and they occur near the ocean surface. That's why they're called surface currents. Now there's 3 different things that affect these surface currents. The 3 things that affect surface currents are global winds, Coriolis effect, and continental deflections. Let's start with global winds. All of these are winds that blow across Earth's surface. These wind patterns are constant, they're steady. They don't blow one day and then not the next. They're all the time blowing across the top of the water. Coriolis effect is something that happens because of the spinning of the Earth. It causes the currents to curve from a straight line. See, ocean currents want to flow straight, but because the Earth is spinning, it causes them to curve. And then finally, continental deflections is when the currents change directions because they bump into the continents, almost like they're playing bumper cars with the continents. And if you've ever been in a bumper car, you've seen that happen, where you're going in one direction and then you hit a car or a wall and it causes you to change directions. So all 3 of these things affect these surface currents that are on top of the water. On your paper, underneath your chart, there's a question that says, how does water temperature affect surface currents? That can be answered here on this slide. What happens is that warm water currents get their warmth from the equator, and they carry that warm water up to the rest of the ocean. The opposite is also true. Cold water currents get their coldness from the poles, and they carry to the rest of the ocean. This helps balance out the temperature of the ocean. If this didn't happen, then water at the equator would be boiling hot. Nobody could get in it. And the same is true of the poles. They would be freezing cold, frozen, and there would be no water there. So the fact that these currents move water around the ocean, it keeps it all at a steady temperature. Here we see the same map that you have on your page. Please pause the video here and color code your map so you'll know which currents are warm and which are cold. It's not necessary that you use red and blue. If you don't have those 2 colors, you can use any colors you want to color code. Now we're going to move on to our second kind of current, which is called a density current. Now this is one of those things that you'll see worded different ways. Some places refer to them as deep currents. I will tend to refer to them as density currents, but all they are stream-like movements of water far below the surface. So again, they are currents in that they're kind of like little rivers in the ocean, but the last ones we talked about were on top of the water. These are deep down below the water. Because they're underwater, they are not controlled by the wind like surface currents are, the ones we just talked about. Because if you think about that, it makes sense, right? Wind can't blow underneath the ocean. It can't go inside the water. So deep currents are not affected by the wind. The next question on your page says, where do density currents form? And density currents are going to happen wherever the density increases. Now we've talked about density before, and when things are more dense, they sink. When things are less dense, they tend to rise. So what causes then the density to increase? Let's look at the next slide. So these 2 things cause density to increase: temperature and salinity. Now what temperature means is that if the water gets colder, let's say it's coming from the poles, that water is heavier, and so it's going to sink compared to water that's warmer than it. So cold water will always sink, warm water will always rise. The other factor here, salinity, is something we've talked about in our last unit. Salinity, remember, is just how much salt is in the water. So the more salt that's in the water, or higher salinity, causes that water to be denser as well. So higher salinity water will sink because it's more dense than less dense water. And our last kind of current is an upwelling. An upwelling is the movement of deep, cold, nutrient-rich water to the surface. Upwellings are really important because they bring nutrients to the surface, and up at the surface is where all the plankton are. And remember, plankton can't swim where they want to go. They only kind of float or drift wherever the current takes them. So they can't go get their own food. So they depend on these upwellings to bring nutrients up to the surface where they are. There's several different reasons why water is brought up to the surface. In this picture here, one reason could be is that this movement of water is bumping into the edge of the continent. This looks like a continental slope possibly. And again, kind of that bumper car mentality where when it hits it, it changes directions. Another reason is that because the surface currents are on top moving, in this picture they're moving in this direction, well then it creates room for the water from below to come up. Sometimes we have what's called an El Niño. An El Niño is the periodic change in the location of warm and cool surface waters, and this happens in the Pacific Ocean. This really affects our weather. What it does to our weather is it causes us to have some very unusual patterns, whereas it may be warmer than it's supposed to be for a certain time of year or cooler than it typically is. And because of this, it can affect our rainfall, and it can cause things such as flash floods and even mudslides. So everything we have talked about so far pertains to currents, those little rivers in the ocean. Now we're going to look at waves. Waves have different parts to them, and you see them listed here. The crest is the highest point, trough is the lowest point, the wave length is the distance between two crests or two troughs, that's how long the wave is, and then finally the amplitude is basically half of the height of the wave. We're going to label this wave that you also have one on your paper too. So the top part there is the crest, and that pertains to any top part. So like here's a crest here. If this one continued over here, this would be a crest also. Trough is the bottom. So again, here's a trough, there's a trough, everywhere a trough. Ha ha ha. Amplitude is half of the wave height. So if the height of the wave is from top to bottom, then half of that would be the amplitude. So that's what this little line here represents, is that it's half. So there's the top of the wave, here's the bottom, so half of that is the amplitude. Now, one way we measure waves is frequency. And frequency is the number of waves that pass a point in a certain amount of time. This will tell us how fast the water's moving. So what we see here in this top graph, it's a little blurry and kind of hard to read, but it's counting by fives. So here, I can't write very good, 5, 10, 15, 20, 25, okay? So what we're seeing here is the same amount of time between both waves. So this top one is a wave and this one is a wave too. But we see that one has a higher frequency than the other. So if we count the crests, we have 1, 2, 3, 4 waves in, what is that, like 25, let's say it's seconds, 25 seconds. Now down here in this second wave, we have 1, 2, 3, 4, 5, 6, 7, 8, let's just say 9 waves, also in the same amount of time. So this bottom one has a higher frequency because it has more waves in the same amount of time. Now, like surface currents, most waves are formed by the wind because we're talking about the top part of the water. What happens is this wind causes the energy to move through the water. So the water itself is not actually moving, it's the energy that's moving through the water. So in this picture here, what we see is this boat. Now, these would be the waves, of course. It looks like the boat is sitting on top of a crest. But when the wind blows, the water is not moving forward, okay? What it is the energy that's moving through it. So this boat, as these waves pass underneath it, all this boat is going to do is kind of bob up and down. It's not going to move because the water itself is not moving. The water's kind of moving underneath the boat. Alright, so far we've looked at currents, which we've had surface currents, density currents, and upwellings. And then we've looked at waves, and our final movement in the ocean is a tide. Now this one's a little different than the other two. A tide is the daily change in the level of the ocean water. So when we're talking about tides, we're talking about the whole entire ocean. Currents are only, in certain parts of the ocean. Waves are only in certain parts, but tides affect the whole entire level of the ocean water. Tides are not caused by anything down here on Earth. They're actually caused by the gravitational pull of the sun and the moon. They work together. The way that a tide works is whichever side of the Earth is facing the moon is going to have the strongest pull. So in this picture here, we see that this side of the Earth, of course, is facing the moon. So that's why that side is in high tide, because the moon is kind of, think of a tug of war. It's like a magnet. It's pulling on the water, so that's why that area is in high tide. But it's also slightly pulling on the land. So when it does that, imagine if there's like a rope, here. The moon is tugging on it, so it's tugging on the water, but it's also slightly tugging on the land, which also creates a high tide on this side, because this side is being pulled away from its water as well. So the same tide always happens on opposite sides of the Earth. So if there's a high tide on this side, there's a high tide on this side. And that's why there's a low tide here and a low tide here. Another measurement we take with tides is called the tidal range. And this is the similar term that you might use in math class when you talk about a range. It's kind of the distance between two numbers. So in a tidal range is the difference between the levels of ocean water at high tide and low tide. So for example, what that means is you can measure how far the water comes up on the shore at a high tide. So let's say it comes up 20 feet onto the shore. Well, at low tide, it's not going to come up that high. Let's say it only comes up 10 feet. So the tidal range is the difference between those two numbers. And from your math class, you know that difference means to subtract. So in that example, the tidal range would be 10 feet, because that's the difference between 20 and 10. So here's a situation for you to practice. What is the tidal range of an area if the high tide is 20 feet and the low tide is 15 feet? You could probably figure this out in your head, but if not, pause it and work it out. And the answer is 5 feet. So all we did was subtract those two numbers. At certain times of the month, though, we have special tides, because remember the tides are caused by the moon. So this is in direct correlation with the moon phases, which we haven't talked about yet. That will come up much later in the semester. But this will be a good intro for you. So we have two special kinds of tides because of the moon phases that happen every month. And the first one is called a spring tide. A spring tide is when you have an increased tidal range, and this happens 2 times a month, one at the new moon and one at the full moon. So on your paper, there's a spot to draw a spring tide, and the way that a spring tide works is all three, sun, moon, and earth, always line up in a straight line. So one easy way to remember this is they both start with S. Spring, straight line, okay? And what this does is it kind of causes the sun and the moon to kind of gang up on the earth. So now both of them are pulling the water. I'm sorry, I drew that the wrong way. Both of them are pulling the water, towards themselves, okay? And they're kind of ganging up on the earth. So it creates a high tide that's much higher than it normally is, and a low tide that's much lower than it normally is, okay? I'm going to erase that. So for a spring tide to happen, they all three have to be in a straight line. Now, it could also be that the sun and the moon are on this side as well. It doesn't really matter what side as long as they're in a straight line. And the second kind of special tide is called a neap tide. This is kind of the opposite. A neap tide is when you have minimum tidal ranges, and this happens at the first quarter and the third quarter. So in a neap tide, the lineup looks a little different. This one, they form a right angle, okay? And so because of this, they're not as strong. Now they're almost kind of working against each other, right? The moon is pulling this way, but the sun is pulling this way. So it's kind of like they're canceling each other out almost. So your high tides are lower than they normally are, and your low tides are higher than they normally are. So you barely have a tidal range. When these happen, you almost can't even tell the difference between high tide and low tide because they're so similar. And then the last thing we're going to look at is kind of a fun fact. There's a place in Nova Scotia called the Bay of Fundy, and it has the greatest tidal range in the world. Now remember, tidal range is the difference between high tide and low tide. So in the picture here on the left, this was taken at high tide, all right? So, you see the water in there. It's come all the way up. You see the boat is sitting in the water, and it comes, way up here onto the shore. This picture was taken at low tide. So what we see is there is no water here in this bay. The boat is on dry ground. And even if you look way back here in the distance, this is all dry ground too. So it's crazy how much the water goes back. And this happens twice a day. High tide and low tide happen twice a day. So this is a daily occurrence for these people.